This microlecture is on combustion and gasification. When you have an opportunity, please visit the attached link for turbine biofuel and watch their YouTube video as well. This is a fascinating spin on thermal conversions because instead of worrying about extractions on an oil-rich algae, they just use the entire algal cell as fuel. It turns out that dried algae powder has the right density and size to be aerosolized and then fed into a turbine as a fuel vapor. The oil content provides a high BTU value, and the algal cell wall just adds to it. They are currently continuing trials to see if algal powder might someday be able to fuel commercial airplanes. This is a very clever thermal application for algae. Please take a moment to review this week's learning objectives. This week we are covering thermal conversions, our second biomass conversion pathway type. There are many different types of thermal conversion products. Thermal conversions can be used to produce solid, liquid, and gaseous products, and a wide variety of each type depending on the reaction conditions. Unfortunately, it can also be a very confusing field because a lot of the same products have different names that would lead you to believe they are not even related. Some of the names of common products are shared here, and as you learn more about thermal conversions, you will better understand what they are and what they aren't. I am going to repeat myself here because this is very important. When we think about thermal conversions, it will be important to think about heat and oxygen. This is because heat and oxygen almost completely control what kind of thermal conversion will occur. As you add more oxygen and more heat to the process, you get different types of thermal conversion. The lowest level of conversion is pyrolysis. It requires no oxygen and just enough heat to start getting biomass molecules to break, so around 400 degrees Celsius. The middle level of conversion is gasification. It requires more heat than pyrolysis, but importantly, it requires the addition of a small amount of oxygen, not enough to combust, but enough to lead to the formation of partially oxidized gas products. The highest level of conversion is combustion. When you give the system all the oxygen it can handle and enough heat to set it off, it combusts, just like a match. Another interpretation of this graph has to do with heat release. Assuming the temperature of the system is in the pyrolysis zone of 400 degrees Celsius or more, addition of oxygen will cause the biomass to leave pyrolysis and go to gasification, and then with more oxygen move on to combustion. However, each thermal process releases heat as well, so in pyrolysis a small amount of heat is generated, then in gasification more heat is generated, and finally in combustion the most heat is generated. The type of thermal conversion is defined by the desired product. If you want heat, you want to use combustion. If you want gas, you probably want gasification. If you want liquids and solids, pyrolysis is most ideal. None of the conversions is really good at making things other than its primary product, so it makes the most sense to figure out what the desirable product is and then find the appropriate process. Thermal conversions of biomass do not occur in isolation. It is almost impossible to separate biomass pyrolysis, gasification, and combustion entirely. All thermal conversions are optimized for a type of thermal conversion based on a desired product, but that only means that of the various products, the primary product is produced the most. It never means it is the only product. Remember, thermal conversions are a hammer, and their products are often a little chemically messy. So now back to the match. Inside the match flame, wood pyrolyzes, gasifies, and combusts with increasing temperature and oxidation. It cycles much the way it is shown here in the figure. It costs energy in the form of heat to break wood down into a gas through pyrolysis, but as soon as oxygen is reacted with the gas, enough heat is generated from the formation of carbon dioxide and water to continue vaporizing the wood. So the cycle continues and the match burns through its wood until it is all gone and the match goes out. To do thermal conversions justice, we have to do a little more chemistry. In order to make the diagrams and slides clear, we need to review what the chemical notation and molecular models mean. Please take a moment to read through this list and get acquainted with these very important chemicals and notation. Thinking about combustion can explain pretty much every thermal conversion. We will use the equations shown above to bracket all three types of thermal conversion and show how they relate and how they are different in terms of chemical bonds, chemical products, and heat production. Pyrolysis is heating with little to no oxygen. You still have activation energy, but you don't get oxygen, so pyrolysis doesn't get the benefit of forming oxygen bonds to make heat like the other conversions. Instead, pyrolysis is all about breaking bonds, so overall, pyrolysis requires lots of heat and does not generate it in excess. Gasification is heating with oxygen, but not enough oxygen to make carbon dioxide and water. Instead, gasification forms carbon monoxide and hydrogen. Therefore, it gets some of the heat benefit of the bond formation, but not much. Gasification certainly generates more heat than pyrolysis, and in fact can generate quite a bit of heat if properly controlled, but not enough heat to be a self-sustaining reaction like combustion. Gasification is right in the middle between pyrolysis and combustion. Combustion is heating with enough oxygen to get maximum bond formation from the production of carbon dioxide and water. This generates by far the most heat, and enough heat in fact to be a self-sustaining reaction as long as fuel is provided, just like the match. Humans use combustion primarily for heat and light. This includes campfires, gas stoves, gas turbines, steam turbine power plants, hot air, hot oil, etc. If you really want to get crazy, look into why light is formed from a flame and how the colors change from combusting different things. Another good puzzle is where the heat comes from. An increasing number of researchers believe, like Einstein did, that chemical reactions are capable of converting mass to energy at a very low level, and that is why they generate heat. The opposing camp says that this is impossible and has no explanation for the heat. It is a debate that will likely continue until we have the technology to prove otherwise. In general, it is important that you remember that combustion products happen because of complete oxidation. This means they are primarily carbon dioxide and water instead of carbon monoxide and hydrogen. It is also important to consider what is being burned. If it is carbon-based, these will almost always be the products. But if it is not carbon-based, then there can be a variety of other oxidation products, like sulfur oxides, nitrogen oxides, and chlorides. I am going to repeat myself again because this figure makes a very important statement about combustion. Despite its age and simplicity, combustion is an ideal energy production reaction on Earth. Without question, the most widespread conversion from an energy perspective is combustion. We live on a planet full of oxygen, and combustion is king when it comes to making energy. Nearly 60% of all the wood produced in the world was used for fuel in 2012. Not for building, not for paper, but for fuel. 60% is an awful lot of wood, and it's hard to believe here in North America since we burn so much fossil fuel. However, in a lot of the world, wood is the only available carbon source, and it is vital for cooking food and providing warmth. Gasification is primarily used to produce gas, particularly a type of gas known as syngas. This can be done using a variety of different types of reactor configurations known as fixed beds or moving beds. The process can also be air-blown, oxygen-blown, or steam-blown. Believe it or not, but when you have a campfire and you throw water on it suddenly, you generate quite a bit of hydrogen, because for a moment before the fire goes out, you are primarily gasifying instead of combusting. Gasification also happens in a meat smoker, as you try to find a balance between the pyrolysis that makes the meat taste good and the gasification that keeps the fire going. These are the products of gasification. Under ideal gasification conditions, only partial oxidation products would be formed, so no carbon dioxide or water would be formed, just carbon monoxide and hydrogen. Syngas is primarily used for catalysis. It can also be used in turbines for electricity, but its most common use is currently for catalysis and the production of other chemicals like methanol, dimethyl ether, acetone, formaldehyde, and paraffins. The most important components of syngas for making chemicals are carbon monoxide and hydrogen. If you recall from the history lectures, Syngas was used for home heating and cooking before natural gas as late as the 1950s. Humans have been using syngas since the 1800s, so it's not a new thing. We're sort of rediscovering it. This is an example of the two most common types of fixed bed gasification, updraft and downdraft. If the reaction is done by bottom-up conversion, it is updraft. If the reaction is done by top-down conversion, it is downdraft. Updraft can convert wet fuel, but makes a very low-quality gas. Downdraft needs drier fuel and makes better quality gas. Downdraft makes a product high in syngas, while updraft makes a product high in pyrolysis vapors. You generally choose the choice of gasifier based on the available biomass and the desired product. There are types of fixed beds other than updraft and downdraft, but they are by far the most common, largely due to their simplicity. Most of the vehicles that ran on wood in World War II ran on updraft fixed bed gasifiers. These gasifiers generated a pyrolysis vapor that could be utilized by the internal combustion engine. This is in contrast to the people that use fixed bed gasifiers to generate syngas for catalysis. Most of the time, fixed bed gasifiers are used for catalysis. They're downdraft gasifiers because a higher quality syngas is needed. This is an illustration of fluidized bed gasification. Moving the biomass and the bed during the conversion supports much greater conversion efficiencies of biomass to gas. Approximately 85 to 95% carbon conversion is possible. Fluidized beds are much more complex and expensive than fixed beds, but their efficiency is much higher and the quality of the gas is much better, and they can be scaled up much larger than a fixed bed is capable of. So, like all other bioenergy technologies, there are trade-offs depending on the size and type of the biomass resource and the amount and type of product that needs to be generated. So back to the campfire. If you could get the campfire hot enough, you could spray water on it instead of blow air. Burning biomass is commonly done with air to supply oxygen as an oxidant. However, air is not the only source of oxygen. Water and carbon dioxide both have oxygen in them and can be used to burn biomass if the temperature of the reaction is high enough. This is how most of the hydrogen produced industrially is generated. This is an illustration of cellulose breaking into common pyrolysis products, acetone and acetic acid. The addition of heat would cause the pyrolysis into these products. The illustration then shows that these products react with oxygen as an oxidant to form carbon monoxide, carbon dioxide, and hydrogen. The addition of oxygen causes gasification. Alternatively, these products can react with water as an oxidant to form carbon monoxide, carbon dioxide, and hydrogen. The addition of water in this case causes gasification. This is called steam reforming. Finally, these products can also react with carbon dioxide as an oxidant to form carbon monoxide, more carbon dioxide, and hydrogen. The addition of the carbon dioxide, in this case, causes the gasification. This is called dry reforming. When you have an opportunity, please visit the attached DOE Energy Information Administration link on biomass. I would like you to spend some time looking at the data available on this website and making some graphs using the available tools. It is very interesting to consider how much biomass we use for energy compared to fossil fuels, and how much of our renewable energy comes from biomass alone.